In this video, we're going to discuss unit vectors. Unit vectors are a subset of vectors in general, which have specific properties. These specific properties are, one, that they have a length of 1. And this is what unit means. So in the title unit vector, unit means length of 1, or it has unit length. Unit vectors also have no units in the physics sense. So you wouldn't have a unit vector that has a length, a unit of meters or meters per second or newtons or something like that. They are dimensionless in that sense. And in this course, what we're going to use unit vectors for is they are going to describe the direction of some vector. And they're actually very useful in being able to describe a vector in terms of a magnitude and a direction. So to see how unit vectors work, I've drawn a unit vector at the top here, r hat. And this r hat vector, I've broken up into some x component and some y component. And I have shown on the right here that the magnitude of the r hat vector that I have drawn here is 1. So this vector has a length of 1. It has no units on it, so it satisfies our r hat requirements, our definition of being a unit vector. The hat symbol here above the r indicates that it is itself a unit vector. To get a better sense of what is and isn't a unit vector, let's look at a few examples. You are probably familiar with the unit vector I hat. I hat is a unit vector that points directly to the right and has a length of 1. You're probably also familiar with the unit vector j hat, which points directly upward and also has a length of 1. Generically, we can write some unit vector r hat as some combination of x hat and y hat. So if we think about the vector that I drew before, that vector pointed up and to the right, had an x distance of root 3 over 2, and a y distance of 1/2. This was my r hat vector. And in terms of I hat and j hat, I could write the unit vector r hat as root 3 over 2 I hat plus 1/2 j hat. Now, notice that the r hat vector, when I take the magnitude of it, again gives me a length of 1. And the I hat and j hat components tell me how far I need to move in the x direction and how far I need to move in the y direction in order to make the r hat vector. Another example of a r hat, or some unit vector, I'll call it a hat. So I could make an a hat vector, which is root 2 over 2 I hat minus root 2 over 2 j hat. And pause the video and prove to yourself that this vector has a length of 1. You can see that it has no units in that I didn't put meters or newtons or anything on it. Prove that it has a length of 1. And I will do that quickly here. I'm going to draw the a hat vector with the components of root 2 over 2 and root 2 over 2. And if I take the magnitude of a hat, that is the square root of root 2 over 2 squared plus root 2 over 2 squared, which is in fact 1. So this is another unit vector. Okay, Now, if we try to make another unit vector, naively we might think that we could make some other unit vector, I'll call it b hat, by simply adding together other unit vectors. For example, like the unit vector I hat plus j hat. So you might think that this is a unit vector, but in fact, this is not a unit vector because it does not have unit length, right? If you find the magnitude of this, it is the square root of the coefficient here. There's kind of a hidden coefficient of 1 in front of each of these, I hat and j hat. So it's 1 squared plus 1 squared equals the square root of 2, which is not equal to 1. So b hat, this vector I've drawn here, is not a unit vector. In order to be a unit vector, you must have no units and you must have a length of 1. Now, for the unit vectors we've looked at so far, I have simply given you components and proved that those unit vectors or those vectors have a unit length or not in the case of b hat, which is not a unit vector. But imagine that we have some vector that is at some angle relative to the x-axis. So it makes some angle theta relative to the x-axis. I'll call it d hat. So I have some unit vector d hat. I know I am I want this to be a unit vector, so I'm guaranteeing that it must have a length of 1, right? And what I would like to do is be able to write d hat, which makes some angle theta with the x-axis, in terms of its x hat and y hat components. Well, I know that this side, I'll call it d sub x, must be whatever the length of the hypotenuse is, which is 1, multiplied by the cosine of theta. And I know that d sub y must be the length of the hypotenuse multiplied by the sine of theta. So I can actually write d hat as cosine theta I hat plus sine theta j hat. And if you want to check, you can say that d hat equals the square root of cosine squared theta plus sine squared theta. But this here is simply a trig identity that by definition equals 1. And the square root of 1 is, of course, 1. So my d hat vector, unit vector, does in fact have a magnitude of 1. And this proves that d hat is in fact a unit vector. It has no units and it has a length of 1. In general, for any angle theta relative to the x-axis, you can write the unit vector that points in that direction in terms of this cosine of theta I hat plus sine of theta j hat. Even if I take some angle, I have a vector that points over here, right? And I have my axis, and I have some angle theta, such that this is my vector here, and I'll call it f hat. I can still write the components of f hat as the cosine of theta I hat plus the sine of theta j hat. I could also take this angle phi. So if the angle between the negative x-axis is phi, that is phi equals 180 degrees minus theta. I could also write f as the negative cosine of phi plus the sine of v, where this is the I hat and this is the j hat. Now that we've seen how to identify a unit vector and to create a unit vector based on an angle, let's take a look at how we can use the idea of unit vectors to make writing vectors slightly more efficient. So let's imagine that I have a 5 Newton force. So I have some force with a magnitude of 5 newtons, and I know that that force acts in the direction of f hat, my unit vector above. Well, I can write my force F as 5 newtons multiplied by f hat. That is to say that I'm writing a vector which has a magnitude of 5 newtons and a direction that points in the direction of f hat, where the components of f hat are given by my cosine theta I hat plus sine theta j hat. So I am writing the f vector in terms of a magnitude multiplied by a direction, where the magnitude and the direction are separated from one another. If you multiply these together, this looks like 5 newtons multiplied by the cosine of theta I hat plus the sine of theta j hat. And multiplying this out, I get that f vector looks like 5 newtons times the cosine of theta I hat plus 5 newtons multiplied by the sine of theta j hat. And this looks like a normal vector that we might have written in physics 1, right? It has some I hat component, it has some j hat component. But often it is simpler to write it in terms of 5 newtons multiplied by this direction, right? We have a magnitude clearly laid out, 5 newtons. We have a direction clearly laid out in the cosine theta I hat plus sine theta j hat. And if I draw this vector, given some theta, I know that this vector must point in the same direction as f hat, right? Because I took just a magnitude, I took a number, right? And I multiplied it by f hat, so I didn't change the direction at all. I just ended up with a vector that points in the direction of f hat, which has a length of 5 newtons. Now that we've seen how we can build a vector out of a magnitude and a direction, let's see how we can break apart a vector into its magnitude and direction and write it as a magnitude multiplied by a unit vector. So for example, let's assume I have some r vector, which is a distance vector because the sides have units of meters. And I want to be able to write this as some magnitude multiplied by a direction. That is, I want to be able to write r vector as some magnitude of r vector multiplied by r hat, where r hat is a vector that points in the same direction as r vector, but has a length of 1, right? So r hat would be something like this. It would be a vector that points down and to the right in the same direction as r vector, but it has a length of 1 and no units of its own. So it doesn't have units of meters like r vector. Okay, well, step 1 is we could find the magnitude of r vector. And I'm actually going to write this out explicitly as 7 squared, the square root of 7 squared plus 3 squared meters. I'm not going to plug that into a calculator and take an approximation of it, because it will turn out in the end that if we want to prove that r hat has a magnitude of 1, we need the exact magnitude of r vector. Okay, so if we want to find r hat, let's try solving this equation here for r hat. It gives us r hat equals r vector divided by the magnitude of r vector. if I write this out explicitly, it looks like 1 divided by my magnitude, which has units of meters, multiplied by 7 meters I hat minus 3 meters j hat, where the minus sign comes from the fact that our 3 meters points in the negative y direction, right? And notice that I have a meters on the bottom and each term on the top has meters. So I have lost the units for my r hat, which is one of the requirements to be a unit vector. The other requirement is that it has a length of 1. So let's find the magnitude of this r hat vector. So the magnitude of r hat looks like 7 divided by the square root of 7 squared plus 3 squared. And that term is squared plus 3 divided by the same denominator. Right, all I'm doing is I am taking each term of r hat and squaring it and then adding them together. And you'll notice that this goes like 7 squared. They each have the same denominator, so I can combine the numerators. And you get the square root of a number divided by itself, which is always going to be 1. So the magnitude of r hat, when I define it this way, is in fact 1. And so if you want to make a unit vector out of any given vector that you have, particularly if you can write it in an I hat plus j hat form, you can simply use this formula here. You take a vector and you just divide it by its own magnitude, and that basically guarantees that the length of the vector is 1, that the units are going to cancel out, and that the sides will have the appropriate proportions such that it points in the correct direction. So now let's make one other way that we can turn a vector into a unit vector. Let's imagine that you have a vector that is of known magnitude and you know an angle relative to, say, the negative x-axis here. And we would like to write this vector in terms of its magnitude multiplied by some r hat. So I'll call this vector r vector again. And let's say that we would like to be able to write r vector in terms of magnitude times r hat. And I already know that the magnitude of my r vector is 10 newtons. Now, if I just use my trig knowledge, I know that the x component of my r vector is going to be negative 10 newtons multiplied by the cosine of 25 degrees. Negative because it points in the negative x direction, and the cosine comes from our knowledge of trig. And I can write ry as being negative 10 newtons multiplied by the sine of 25 degrees. Again, negative because it points in the negative direction. In terms of x hat and y hat, then I can write r vector as negative 10 newtons multiplied by the cosine of 25 degrees I hat minus 10 newtons multiplied by the sine of 25 degrees j hat. And I can use exactly the same formula that I used before. I can say that r hat equals r vector divided by the magnitude of r vector, which looks like the thing I just wrote divided by 10 newtons, which looks like negative cosine of 25 degrees I hat minus the sine of 25 degrees j hat. And as we have seen before, if I take the magnitude for any theta, right, the magnitude of this vector will be cosine of 25 degrees squared plus the sine of 25 degrees squared, and I square root that. And it's a trig definition that that is equal to 1. So what I can do is I can write r hat as this, and I can say that r vector looks like 10 newtons multiplied by r hat, which is the same as 10 newtons multiplied by the negative cosine of 25 degrees I hat minus the sine of 25 degrees j hat. Now, this is very useful because in this class in particular, we are going to want to investigate systems where we have a vector that points in a specific direction, and we want to be able to write other vectors that point in that exact direction. So being able to pull out the r hat, the unit vector with only direction information, is going to be very useful for us as we move into the electric force. And we have learned how to be able to do that from a vector where we know the magnitude and the angle, and we've also learned to do that from a vector where we just know the components of the different sides. We also learned that we can write down a vector, if I know a unit vector, that I can write down a vector of any length which points in the exact same direction as a unit vector by simply taking some magnitude here and multiplying it by the direction that is given by the unit vector.